You on? Okay. All right. So I'm going to be lecturing for Professor Eager today. My name's Brian Holman. So my background, I worked for a consulting company the past 5.5 years. I just started my own consulting company up here recently. But a lot of what I do deals with materials failures, and a lot of issues sometimes deals with material substitution. So that's going to be the topic of today's lecture. And the first example we have is going to be a refrigerator. So, I was talking with Professor Eager about this yesterday. Early, when he was a child, the refrigerators were made strictly out of, metallic components. In our lifetimes, we're starting to see they're almost more like computers. You see some of the capabilities of refrigerators nowadays has cameras and things built into them, a lot more electronics. So you've seen the change over time. One of the main material substitution issues that happened years ago was when they switched from metal shelving to plastic shelving. All right, what they initially did was just say, all right, we're going to just mold this out of plastic and stick it in, and it'll save us a ton of weight. And one of the things here is you see that when you're working with a system, you can't just look at either one property or one particular aspect of the system. You have to look at everything in a whole and how it interacts with each other. So what happened when they switched from metals to plastics, and there's a lot of case studies on this, was they were getting a lot of cracking in the plastic shelving themselves. So what was happening was, if you went from all metal to metal system, if you start thinking about thermal expansion, thermal contraction, and stresses when things are joined together and constrained, when this was all just made out of metal, you didn't really have an issue because it was similar material and it expanded and it contracted at the same rate. However, when now you're going to make this out of dissimilar materials, if you have metallic slides here and plastic shelving that has a metallic outside to it, now you're going to be adding all these other stresses to the system while it's in service. And what was seen, if you look closely, you can see what they're getting is because you're constraining the plastic by this metal piece here, all right, now you're getting stresses on the plastic while the cools and when you open the doors, things like that. So they were seeing a lot of these plastic shelves were cracking because of the material substitution. All right. So this was an issue where the designers didn't take into account the fact that, all right, it's going to save us weight. Yes, plastic is not as dense as metal. It's cheaper, it's cheaper to produce. But when you put a component into service, you have to look at the whole array of functionality that it needs to provide. So what was overlooked in this case was when you have dissimilar metals and you join them together, you're going to create stress concentrations. And in this case, what happens is you have the plastic joined to the metal, all right, and then these things are expanding, or cooling, contracting at different rates in service, and you're getting cracks over time. So this was an issue with the substitution, of a refrigerator. Now you said you worked at a refrigerator. Did you have any issues while you were working there related to cracking of components or dissimilar, or was it more from a?
Sometimes they would crack during assembly.
Yeah.
But I don't think that there are many recalls.
Yeah. So we have other examples we're going to get to. This was the first one. We're going to talk about what this happens when you talk about gas lines, when you talk about water mains, and when you're actually conveying material from one area to another. All right, so to continue, when you have competition between different materials, Professor Eager discussed the economies of these different materials, steel versus aluminum, in terms of mass tonnage and how much manufactured components of each are made per year. But when you're talking about competition between whether you're going to select a metal or plastic or glass, all right, you have to think of the whole array of the environment the component's going to be in, how much unit cost you want to produce it for, other issues such as weight, brittle, if it's brittle or not, impact resistance. So you have a whole suite of mechanical properties that you need to keep into account. So the one that everyone knows as an example is food containers. All right. So initially, if you've ever seen a 1950s Coca-Cola bottle, it was made out of glass, and that's because the technology for polymers wasn't around in the 1940s and 50s to make them out of polymeric materials. But over time, as the technology matured, you can see that there's a competition, and the issues with glass were it was heavy and it was brittle. You dropped it, it broke into thousands of pieces. You change to a polymer, it's impermeable, it has more resistance, and it's a lot cheaper to make. But one of the things, I don't know if you guys notice, is with your water bottles over time, they're trying to optimize weight savings and things. They've actually made the plastic thickness layer thinner over time. And they've actually had issues where, they've made them so thin that failures have happened during transportation and packaging. And these are things that happen when you're, substituting from one material to another or from one design to another of the same material. So you can see, these things, they're getting to the point where there's not much thickness to them. So you have to take these things into account transportation-wise, how point A to point B, and ease of use, things like that, recycling, composite costs, corrosion. When you have your soda can, Dr. Eager talked about that soda is basically phosphoric acid, right? So you have to make sure that the soda wouldn't react with whatever material you're going to place it in. So you wouldn't use a carbon steel soda can. You'd use something with a little more resistance to it. So the material substitution also happens over time. All right, one of the best examples is conveying of water. So we're going back, if you look at the top left figure here, clay pipes in 4000 BC. And why did they make them out of clay pipes? Because that was what was available, right? You didn't have steel mills, you didn't have factories to make these things. So some of it is the product of the era you're in. So we talk about the aqueducts and the Roman Empire, how they changed into more concrete type aggregate structures over time. Now we're getting into the period where they transferred from more concrete material to wood and cast iron. All right. And today you're seeing these large cast iron pipes or ductile iron pipes in a lot of these major cities. They're 100+ years old. And one of the things that happens with cast iron over time is it can become embrittled, and you can get stress cracking and issues just by it being so old. So one of the things you're seeing is as infrastructure ages, now they want to go in and put in the latest and greatest materials. They want to switching to more polymeric type materials as well. So there's a competition between what was in the ground, what you're putting in the ground, and sometimes you have to think about the design. If you're going to switch from a ductile iron pipe to a polymeric pipe, you have to take into account, like I said before, you have things, this is going to be in the ground, so you have to take into account the environment that it's going to operate in. All right, the soil could be acidic, depending on which location in the U.S. you're in, or there could be trace elements from factories in the soil itself. So that's environmental factor. You have to also take into account corrosion resistance. So one of the things is, the polymers have very good corrosion resistance generally. Heat temperature issues, it's going to be how hot, what type of water you're going to use is going to be ambient temperature. And this is not just for transmission, this could be going into your house, plumbing connections, things like that. So the conveying of water is a good example on how we went from different materials, starting in 4000 BC with the clay pipe, because that was the technology that was available, to a concrete aggregate type material, stones, to wood, and then later on, cast iron, ductile iron, plastics. And in addition to not only conveying water, you can, another example is conveying gas. So this image up here is actually, that's wood. That's years ago, they used to hollow out wood trunks and gas would be transferred inside of these. Now you can think of, who can think of some issues, with wood over time and having a combustible material flowing through it. But that was really, in the 1800s, that was, or when they were first getting things started, that was a main issue. All right, one of these things now we're seeing, you have fractures, you have different types of gas pipes. You can have plain carbon steel, and you guys have probably seen in the news over time, 100-year-old pipes that break and it's major inconvenience and things like that. So it's an issue of, once it's in the ground, are you going to maintain it? You're going to leave it in place? You don't want to have to go in and dig this stuff up every 5 years to inspect it. So one of the other issues is, as you substitute from one material to another, how are you going to inspect this over time to make sure that it's still, functionally and structurally sound? And after we go through these few slides that Dr. Ida put together, I'm going to show you some examples on how you can test the component and how to actually determine its mechanical properties. So we have a whole bunch of examples here on pipe. This is pipe. This is for gas. This is a plastic HDPE, high density polyethylene pipe. They're now using these types of pipe in the ground in various locations rather than using metallic pipes, either carbon steel or whatever. They're going to these plastic pipes because, for one, they're easier to fabricate in the field. So I had a job a few years ago where they asked me to look at this style of HDPE pipe, and what happened was it had fractured, and they wanted to know, was it an issue with the pipe or was it something that happened while they were doing the production process. But the thing about this pipe is, they actually, for the job I was working on, they had thousands of feet of this pipe out on a barge out on the Hudson River, and they were actually fusing it and running it under the river in place. So this is something you couldn't do out on a barge with metallic pipe. So there was flexibility while they were actually putting it through, boring through the hole and tugging this along behind it. But the reason they could do that is because this joint right here is a fusion welded joint. So they heat it up and they basically press it together and fuse it. And they continually just feed this off the barge while they're pulling the pipe in the ground. So for a contractor or somebody who's installing it, this is a lot easier than having to do it piecemeal with a metallic component, weld it. If we're talking about pulling something under a river, how are you going to dredge a river? So one of the things is you're starting to see more plastics because of the ability, flexibility it provides when you're installing it. But there's some issues. I mean, one of the things is, have there been any studies, to see how this will be 100 years from now? And generally, these stuff is not performed. You can do an accelerated test, but you have to make some assumptions. And these hasn't been in service. I mean, they've probably only been using these maybe 10, 15 years. So you're going to start to see, like with anything, when you start to substitute a material, there'll be unforeseen, environmental conditions, field conditions, and we'll see how the material responds over time. Another example, Professor Eager gave me this yesterday. So he's having a renovation done on his house. Have any of you guys ever done any soldering or either jewelry or things like that? So if in your house, everyone has plumbing, and years ago, all the plumbing was joined together by lead tin solders. All right, but over time, what happened was there's environmental restraints on the lead, things like that. I don't know, you've probably seen all over the news all the people up in arms over the lead in the school drinking water, and that's a result of the pipes having lead joints, and they probably had lead in the composition of the pipes. They're so old. But the plumbing used to be lead tin solder connection. All right, now they wanted to get away from the lead in the tin, so the EPA or other government agencies said you can't use certain fluxes anymore. So they moved to different materials, but those materials had their own issues. They didn't form as good a joint, so you got a lot more leaking, or they became brittle, with higher temperatures, things like that. So Professor Eager gave me this, and he said this came from the remodel of his house. And now what they're doing is they're doing almost like a swage connection, where you don't even do solder, any type of solder joint anymore. It's a swage where it locks into place. So this would be for your plumbing connection going in your house to either your sink or things like that. So now they're trying to get away from even having to do any soldering. And one of the implications, we talked about externalities and costs. At least in where Professor Eager lives in Belmont, if you want to solder, all right, you have to get what's called a hot work permit by the city. And then with the hot work permit, if you're doing welding or things like that, there's sparks, right? So you have to get a special permit to do the work, all right? And then the other thing you need to have is what's called a fire watch. So there's cost implications as well. So if you need to have somebody from the fire department and you have to pay them when you're soldering these joints in the plumbing, versus just saying, all right, I can go buy this at Home Depot or one of these major retailers, and all it is a snap connection and leave it in place. Cost really is the driver for a lot of the construction activities and joining activities. All right, so the next one here is what's called corrugated stainless steel tubing. All right, CSST. Now, this was an issue because a lot of the home contractors wanted to go away from just black iron pipe, which is this. So this is what used to be a threaded pipe that would, the gas connection to your house. This is where the gas would come in through just a black iron pipe. One of the reasons they wanted to get away from it is because this is more flexible. So rather than having a threaded connection and having elbows and T's and everything, they could use this material, which has some flex to it, okay? So there was a switch between materials. They went from this material to this material. But what happened was they started to see houses were burning down. And the reason why some of these houses were burning down was because when they manufactured this material, the wall thickness of this material, and this is the sheath around it, the insulating properties of the sheath and the wall thickness, when some houses were getting struck by lightning or lightning was hitting the ground, the energy was enough to actually puncture the wall. So now you have a gas line, you have a source of combustion, being the lightning strike arc, and you have a wall thickness that is thin enough that it can be punctured by the lightning strike. So what you're seeing here is actually taken from a site where they had puncture in this line and a fire resulted. So one of the things is when you substitute materials, you don't know, did a designer take that into account? When if I'm switching from this to this, the wall thickness is going to be critical, right? Because you can't have a material in your house and people's houses are going, the chance it could go, up in flames if it gets a lightning area. So one of the things, and if you watch TV, some of the commercials, these, over time you have recalls, whether you have automobiles, things like that, you have recalls. And a lot of the times the recall is a result of your material substitution or a design issue where you switch materials. Yes.
Have you been following the Samsung thing?
With the iPhone 7 or
This
the
Samsung
Note.
phone that's like catching on fire.
Yes, and not only that, actually, I've worked on some cases where you have the phones catching on fire, but a lot of these people do the vape pens, all right, because they think it's a safer alternative to smoking. The vape pens have the same issue that they can spontaneously ignite. You get what's called thermal runaway on the battery. So some of you work in batteries, or some people. Does anyone here do batteries? So I mean, one of the things with your battery, you want an energy density that you want to get as high as possible. We talked about these Ashby charts where it's two different properties and it's a trade-off, right? So you want to get the energy density up, but do you want to talk about some things you've seen in terms of the fire protection or charging, discharging?
You don't really feel that too much, but it's basically if you start running the battery too hard beyond what it's designed to do, and it heats up too much, then it's sort of a self-fueling process where
And
it just gets hotter and hotter.
Yeah.
And at some point you have an organic in there, and it becomes basically a fuel for a fire.
So, one of the things I read in the news was Samsung's response, when they recalled whatever 1.2 million phones or something, was to tell the consumers don't charge it past 60%. So that ties into to keep the temperature down so it doesn't get so hot where you'll get combustion. So you see this in all. One of the other things I've seen is with glass, with the battery casings. So I've worked on glass failures on a lot of structural glass, like panels on large skyscrapers and things like that. And there's issues with that in terms of you can get glass breakage because what you have with glass is called a IGU, insulated glass unit. And generally it's more than just one panel. It's multiple panels tied together. So if you think of that as composite, right, like a sandwich put together, you have a small gap space between the IGU glass layers. And one of the things they've seen is by designers trying to optimize things so much that they've made that gap layer smaller and smaller and smaller. But what's happening, you've seen in some buildings, that when the sun hits it, in the morning, you get your thermal expansion and it gets hot in those layers. And because the design has gone to try to optimize to minimize the whole unit thickness and weight, that you have such a small space, it's getting hotter and hotter, and the heat can't diffuse out, and you get thermal stress breakage. So you've actually seen, I've been on sites where you've seen panels like shattered. Now they tie in extra safety so you don't have panels falling 80 stories down on people, right? Because it's a life critical component on the curtain wall. But you have to think in terms of the whole system, all right? Think in terms of temperature, you think in terms of what the emissivity of the glass will be. You want to get, credits, environmental credits on these large skyscrapers. This can be millions of dollars by using a certain type of glass versus another. But if you then have, panels breaking, in the long run, is it worth it or not? I wanted to spend the last few minutes, the last second half of the class today, to talk about some projects I've worked on, and not just generally material substitution, but inspection and testing of structures. So how many people take the T or, ride the T? Generally, I take the T in every day. So I take the red line in, and we talked about the size of steel industry, and how trains aren't run on maglev here, things like that. So the miles of steel that all these train systems around the U.S. run on, it's enormous. So one of the things is what happens when you have, steel that you have trains running on daily, and you have to leave it in service 80-something years. I mean, has anyone ever been inconvenienced by, a train issue? So one of the things when I take the T in and I look, I think of it from a maintenance perspective, and I've worked on train derailments where you actually see the fractured rail afterwards. And some of the things that are interesting is with trains, you get a lot of issues, fatigue a lot of times with the rail, because you have the train truck is running over it. And if you think of your train system, you have the rail, then you have ballast underneath, which is your concrete and your aggregate. And then that's allowing for water to drain out. But this is a structure, you have hundreds of thousands of pounds that is being transported over the steel. So there is some flex to the steel. I've seen on some rail systems where you have cracks, and you can actually see the fatigue crack has grown because of all the cycles that go on it. So you have to be able to go in and inspect stuff like that. The transit agencies have a system they call a Sperry car, and it's a car with an ultrasonic sensor on it, and it actually at night, when the trains aren't in service, it runs over and it looks for indications in the rail to see if you have cracks in it or not. So the example here I'm going to pass out. This is not from a commuter rail. So I don't want you to think that somebody was, driving on this. This was from a crane rail. So this was a rail that was out on a barge, and it was a turntable, and a crane actually moved over it and did dredging operations. So I got a call one day, and they said, we need you to come out here. We can't run the crane. The rail broke. So we flame cut the section of rail out that I needed, and then when I came back to my lab and cut a clean section through it, I saw this. Now, do you guys think this should have been here? All right, what this is called a forging burst, and this happened during the manufacture of the rail. So a lot of times you have hot steel, molten steel, you need a refractory when you're manufacturing it, right? So chances are maybe some of the refractory fell off, some of the brick casing that keeps the heat in the steel when the steel's molten. Chances are a piece of it fell off, and when the rail was getting extruded out, this area never melted because you had a refractory there that's melting temperature is above what the process temperature is. So one of the things that should have been done with this rail that I don't know if was, though, before this rail gets put into service, you should do what's called UT, an ultrasonic inspection on it. And the ultrasound, it's the same as if a woman goes to a doctor and she's pregnant, it deals with sound waves, same as like your sonogram. So the ultrasonic inspection, you use a couplet material, and what should have been done was you put the couplet material on and then you check the consistency of this with sound waves, so it goes through, and you would have gotten an indication that showed that this was here. But this got put into service, so ultimately they had to replace that whole section. Some other examples, you have huge pressure vessels and pipelines and things like that. Over time, if you wanted to see the integrity, how the steel's holding up, things like that, you can do mechanical testing. How many of you guys do mechanical testing in your research? Compression tests, tensile tests, things like that. So this is a structural materials class. When you're dealing with steels and thick section structural materials, one of the things is your Young's modulus, ultimate tensile strength, elongation. These are all properties that are, for the most part, probably going to be most critical for structural applications. So when you're doing tests, you want to actually take samples and do testing. This is a blank for a round bar tensile test. So this would go in a testing machine. This gets threaded into grips, this gets threaded in the grips, and you'd pull it, and this will tell you, this will neck down over time, and it'll tell you what your tensile strength, your yield strength is, to tell you if the raw materials, once it's fully fabricated, is as strong as it's supposed to be. So for any skyscraper or any large structure, you want to test the metal to make sure the quality of it is what it should be. Now, one of the students the other day asked about wire rope. So the same as you can do a tensile test on this material and watch it, neck down, I'm going to show you guys a video of a case I worked on a few years ago. It was off a cargo container ship, and they have wire ropes for, lifting, huge amounts of weight onto the container ships. So one of the wire ropes fractured, and they wanted to know, if it was a material issue or not. So this is a full-scale test I'm going to show you guys of the wire rope. So one of the things to notice, and let me see if I can. Anyways, I'll have to show you this way. So, all right, one of the things you'll see here is this testing setup is 3 stories high.
Slightly better, yeah.
Actually, maybe I'll just pass this around. Afterwards, the wire rope, the machine that was actually testing this was 3 stories high. And the connections the rope section itself was probably about 12 feet. So one of the things is, this rope was probably an 1.5 inch, 2 inch thick diameter. So this is really strong, and the way it's braided, the way they braid the metallic wire rope makes these things extremely strong. So one of the things, we tested this and it broke over 300,000 pounds. It took 300,000 300 KSI when it broke. So I don't know why it's not playing on there, but
Did you put it on full screen?
let me
If
see.
you take it off full screen, it might play. Sometimes it goes out of presentation.
You did try Windows key and P and do P.
Is it like a YouTube?
No, it's a movie video. So, anyways, there are YouTube videos out there that show these wire rope tests they do at the manufacturers. So this one was the one I performed. The setup was vertical, so it was 3 stories. At a lot of the manufacturing facilities, you have size constraints, so they set it up horizontally and do those tests. Another type of test that you have to do, we talked about fracture toughness, is a Sharpie impact test. So all right, so if we're talking about fracture toughness, okay? If you have a pressure vessel or any type of critical component, you have to make sure that if it gets a crack in it, it's not going to brittly fracture. So what was 1901, all right, you'll see how simple a test it is because in 1900, you didn't have computers and couldn't do crazy, simulations. So this test is basically a test where you have this swing, you put your Sharpie sample in the holder, and you can do this at different temperatures. So you could put this in a bath and just let it sit for 10 minutes and take it out and then test it. And you can test at different temperatures because your impact toughness is a function of your temperature, right? So you have to make sure that you'll have impact toughness throughout the range of temperatures you're operating in. And basically, you set the sample in, you swing the hammer, it breaks, all right, and this is what the fracture surfaces look like. And there's a specification group, it's ASTM, American Society of Testing and Materials. They are the organization that comes out with these standards. And it's actually, there's an ASTM standard for how you run this test so that when different labs run the test, it's apples to apples comparison and people aren't just reporting the results they get, that you don't have something to compare to. So if you're putting a structural material in service, you need to meet, certain impact toughness, fracture toughness, and impact strengths. And this is the test you'll do on it. So this is a blank for it. And one of the other things to note is if you look on that, there's a notch. So you notch it in the center so it breaks there. The direction, if we're talking about pipelines or other structural materials, which orientation you notch it will have a big effect on what value you're going to get on your Sharpie test. So that ties into your rolling direction of the steel, if you're going along the grains versus against the grains, things like that. All right, one other example I'll show you guys. We have these are metallurgical mounts. And when you have something that breaks, in general, you want to look at the fracture surface. So you'll go in and when you're dealing with big structures, you have to really go in and section out something that you can handle. So when you take the piece out, normally when you're looking at a structural metal, or you do a metallurgical eval, you would mount it, all right, and polish the sample, look at it under the microscope. But what you'll see here is some indentation. So you can also do micro hardness tests versus macro hardness to see if the hardness is in line with what it should be, and that will tie into your heat treating of the material, annealing, things like that. But one of the other things to note is actually I use these because to show what not to do when you're making the mount. So if you see there's a huge cloudy area in here. So you have to mix the stuff right and you let it set. These are cold mounts, which are epoxy based. So you'd put your material in flat, you'd mix this two component like goo and let it sit for 4 hours. You get a clear mount, or you can do a hot mount where you do it under temperature. So these are various mounts from samples. All right, and the last one I want to show you guys is this would be a CT sample. So sometimes you want to know if you know an airplanes know they're going to have cracks in the wings. But one of the things they want to know is how that crack will grow over time. So that's, yeah, I mean, on the wings of airplanes, they're designed to withstand cracks. Now, there's a critical crack size, but you know, that's the old airplanes that had rivets and things like that. I'm talking more aluminum frame. So now that you have composites, the issues of cracking on a composite are a lot different than aluminum between a carbon. So if you're looking at the Dreamliner versus an airplane from 30 years ago, all right, there's going to have different issues into the design. But if you're dealing with aluminum airplane structure, what you would have done is this is a CT test. So this has the notch in it. You put it in, you cycle it, and then you can actually track the growth of the crack with the cycles. So that's something you want to know, because every time you go on a plane, you have a pressure depressure cycle. So this goes into fracture mechanics and some other things that Professor Eager or Dr. Bellmare will talk about. But when you're talking about fracture mechanics and crack growth, and we need to understand the rates at how these things grow. So a lot of times, you'll design something. Some of the industries say leak before burst. So you want to design it so it's not a catastrophic failure, so that you know you can go in and maintain it before critical fracture occurs. So this would be a CT sample. Yep.
For these types of tests, are there any standards about like simulations you have to run on new materials, or is it mostly just we know the properties and we're going to replace it and then test it a bunch and then?
Well, a lot of times you'll do the actual mechanical testing hand in hand with like a computer simulation type thing. So the ASTM standard or API or whichever standard your material has to conform to will tell you minimum acceptable limits. So the first thing is you run the test, does it meet that? And then you would tie the values you get in there into a simulation if you're trying to predict either crack growth or properties over time, creep, things like that. So there's a whole suite of properties that need to, yeah. You guys can see these too.
Simulations rather than all of these.
Well, the one thing is it costs a lot more, the video of the wire rope. So that's a huge structure. There's the largest one that I've seen is at Lehigh University, and it's a 5 million pound load cell. So they were actually doing full scale, bridge sections where they would test these things to failure. These are very expensive, right? So it costs a lot of money to make a mock-up, to use the equipment. So yes, you want to do as much computer simulations as you can, but at some point you have to benchmark it against an actual value to make sure that you're not putting in a false assumption into your model. So the actual testing, that's done, a lot of times I get involved after the fact, after something's already broken, and it's a question of not we're putting it into service, it's a question of was this material up to what it should have been while it was working, to try to find out root cause on why it broke, things like that. So you need to make sure that the properties, when you need to do some testing, and you can do similar tests on plastics. That this can be done. They actually have a different scale. Plastics operate off of a Shore scale, so and a different hardness scale, and it has different values. But you can also do this for plastics. So if we were looking at the bulletproof glass that Professor Eager showed the other day, if you wanted to make sure those polycarbonate layers were what they should have been, you can do impact type tests on that as well to see what values you get. I guess the only other thing I'll end with today was Professor Eager had talked about for Navy and trying to, you want to reduce topside weight. So these were a couple samples for back when I was doing my master's thesis. One of the things we were looking at with the Navy was, could we use sandwich type structures or composite structures with different materials rather than just monolithic pieces of aluminum on the top side. So we looked at these different structures, and one of the things is, as Professor Eager said, you have to look at the whole array of properties. So we were getting very good compressive stresses with these, where it could withstand good compressive loads. But one of the problems is when you're dealing with this is, bending loads and shear, things like that. And also joining. There's these foams, right? You saw this. This is what's called a closed cell aluminum foam. This is open cell. So what we were looking at was actually doing a what's called a dip brazing procedure, where you put it together, all right, and you dip it in a molten bath of sodium fluoride, take it out, clean it off, and then it's all joined together. But it's extremely cumbersome, and you have to think, do you think the U.S. military would then have to go in, if you had an issue where you had to maintain this, how are you going to, repair these things in the field, things like that? So these are, great novel, boutique type materials, but you have to think of, how do you maintain it? How would you repair it, replace, things like that? So these are these samples here. So does anyone have any questions? Yep.
I was wondering for the NDT, how rig, for instance, like the track that you say had a foraging defect. So the track is probably really long. How are you gonna take samples consistently such that you can prove that this thing is overall structurally sound?
For the rail, it doesn't actually take samples. All it does is it shoots sound waves while the inspection car is rolling on the track, and if it goes past a threshold, so with the ultrasonic sound waves, you have decibel drop, right? So when you're looking at the data, if your reflectance of the sound wave, if you hit a defect, you'll have a drop. So that would be your indicator to then go in and see if you have to do a more precise inspection. So you can always do multiple inspection techniques. Some aren't always applicable to every material. So you have what's called magnetic particle tests, but you can only do magnetic particle tests on a material that is magnetic. So you wouldn't do it on a polymer. You can only, you have eddy current testing. A lot of times on your heat exchangers, you have these really long 20-foot sections of tubes that you have, cooling. You can do the eddy current because it's nice and quick. So you have the same issues you have with material selection, you have with material inspection. All right, so what's the depth of penetration you need to go through to see the defect? Is it a surface defect? Is it a volumetric defect? So there are multiple inspection techniques that they do in the field to try to make sure that they can see if there's a problem or not. All right, so, one more question.
Are these materials, what are they used for? Anything?
I mean, that they some of that might have been used on like a space frame because it's so light. So as a foam on the space shuttle, I think that was one of the uses that they called out. I don't know if they're actually doing it though, but. All right, so Dr. Bellmer will be giving you guys your lecture tomorrow. Thanks a lot.